Have you ever really stopped and thought about the simple magic of a magnet? That invisible force that can just snap things together or push them apart? It almost feels like something out of a fantasy novel. But it is pure physics, and today we're going to pull back the curtain on that force.
So it all really starts with this simple, almost ancient question. Why is it that a compass needle, just a tiny piece of magnetized metal, so reliably points north? It's like it knows something we don't. Well, to figure that out, we first have to understand what that little compass needle is actually feeling.
All right, section 1, the force on a magnet. See, that compass needle isn't just acting on its own. It's constantly feeling an invisible field all around it, the Earth's magnetic field. And that interaction, it creates a force. But it's not a simple push or a pull. It's more like a twist.
And that twisting force has a name. It's called torque. Just imagine you're trying to turn a wrench, right? The force you apply to the handle creates torque, and that's what turns the bolt. Well, for a magnet, it's the magnetic field that's basically the hand on the wrench, always trying to rotate it into a very specific alignment.
And of course, physics has this beautiful, simple way to describe that twist. The torque, that's our symbol tau, really just depends on two key things. First, M, which is the magnet's own internal strength. You could almost call it its magnetic personality. And second, B, which is the strength and direction of that external field it finds itself in. The torque is simply born from the interaction between the magnet's own identity and the field that's all around it.
So, when is this twisting force the strongest? Well, it's at its absolute maximum when the magnet is fighting the field, trying to sit sideways at a 90-degree angle. But as that magnet starts to rotate and align with the field, the twisting force gets weaker and weaker until it completely disappears. The magnet is finally at rest, perfectly happy, when it's aligned and the torque drops to zero.
And this all brings us to the idea of energy. Just like a ball always wants to roll to the bottom of a hill to lose its potential energy, a magnet wants to rotate to its position of lowest potential energy inside that magnetic field. It's just constantly seeking out its most stable, most relaxed state. And this shows us the two extremes of that energy state. When the magnet is perfectly aligned with the field, it's in its happy place, totally stable with minimum energy. That's our compass needle pointing north. But if you were to force it to point completely backward, it would be in a really unstable state, holding the maximum possible energy. It's like balancing a pencil perfectly on its tip, just waiting for the slightest nudge to flip right over. So, okay, we've covered the what and the how of a magnet's behavior. But this whole thing leads to a much, much deeper question. What actually makes something like iron magnetic in the first place, while, say, a piece of wood isn't?
Well, the answer, as it turns out, isn't really in the material itself, but deep, deep inside the atom. The secret to all of this, to all magnetism, lies with one of the most fundamental particles in the entire universe, the electron.
See, down at the atomic scale, magnetism comes from the electron in two main ways. First, think about an electron orbiting a nucleus. That movement of charge creates a tiny little magnetic field, kind of like a miniature electrical circuit. But even more important is a property called spin. You can picture the electron itself as a tiny spinning ball of charge, which turns it into a powerful microscopic magnet. And that intrinsic spin, that's the real secret ingredient for the most powerful magnets out there. So if the electron is the source, is there like a minimum amount of magnetism it can have? And the answer is yes. It's called the Bohr magneton. You can think of it as the fundamental pixel of magnetism. You can't have half a Bohr magneton. It is the smallest possible chunk, the fundamental building block.
Just look at that number. It's almost impossibly small. And yet, and this is what's so incredible, when trillions upon trillions of these tiny quantum magnets all agree to point in the same direction, their combined force becomes something we can actually feel in our hands. It's this amazing bridge from the quantum world to our own.
Okay, so we know the origin story. It's the electron. Now we just need a way to describe how all these different materials react to magnetism. Physicists have a sort of language for this, a few key ideas that let us measure and classify a material's magnetic personality.
First up is magnetization, or M, okay? Imagine a huge stadium full of people. If everyone's looking in a totally random direction, there's no overall direction, right? But if they all look towards the field, the entire stadium is aligned. Magnetization is just like that, and measures how many of those little atomic magnets are aligned in the same direction inside a material.
Next is magnetic intensity, or H. Now, this isn't the field itself, but it's more about the effort the external field is putting in to try and magnetize that material. You can think of it as the cause, while magnetization is the effect.
And finally, this is the most important one for classifying materials: magnetic susceptibility, that Greek letter chi. This one number tells us pretty much everything we need to know. It's just the ratio of the outcome m to the effort h. It answers the simple question: for given magnetic push, how much does the material actually respond?
So, using that concept of susceptibility, we can now sort almost every single material in the universe into one of three magnetic categories. Each one is defined by how its big collection of atomic magnets responds to an external field.
First, we have diamagnetism. And believe it or not, everything is at least a little bit diamagnetic. Even you. It's this incredibly weak effect where a material is actually repelled by a magnetic field. And this is why its susceptibility is negative. It actively opposes the field.
Next up is paramagnetism. So in these materials, the atoms are like tiny little compasses, but without a field, they're all just jumbled up, pointing in random directions, canceling each other out. But an external field can persuade them to line up, which creates a very weak attraction. And that's why their susceptibility is small, but positive.
So the key difference here is the sign. It's negative for diamagnetic materials, they push back. And it's positive for paramagnetic materials, they kind of weakly go along for the ride. But both of these effects are incredibly faint. So where do our everyday strong magnets come from?
Well, that brings us to the superstar of the group, ferromagnetism. This is what we all think of when we say magnet. In materials like iron, there's this powerful quantum mechanical interaction that forces neighboring atomic magnets to align with each other automatically, forming these massive magnetic neighborhoods called domains.
And this is how you actually make one. In a normal everyday piece of iron, all these domains are pointing in random directions, so their effects just cancel out. But when you apply an external field, the domains that are already kind of aligned with the field start to grow and they take over their neighbors. If you apply a strong enough field, all the domains merge into one giant superdomain, and at that point, the material is a permanent magnet.
So let's bring this all the way back around. That compass needle points north because it's a ferromagnetic material. Its magnetic domains are all aligned, creating a strong magnetic moment. That moment feels a torque from the Earth's magnetic field, and that twists it until it finally settles in its lowest energy state, perfectly aligned with the field. And that entire chain of events, it all starts with the spin of a single electron.
It's really an incredible journey, isn't it? From the quantum to the classical world. The secret life of a magnet just shows us how these tiny, hidden rules can build up to create the visible, tangible forces that guide our maps and stick notes to our refrigerators, which really makes you wonder, what other fundamental, invisible rules are quietly shaping everything around us?